I will discuss a set of physical and chemical treatments that affect the electrocatalytic activity of the perovskite catalyst for the oxygen evolution reaction. It's called the BSCF. It is this big structure here. And this paper particularly discusses the effects of ball milling on the activity. It was prepared and published with the Schmidt Group in May 2017. So on one hand, it is pretty new and it is up to date with all the technological advances in the oxygen evolution reaction catalysis, and on the other hand, it adopts a non-descriptor based approach to the problem of enhancing and studying electrocatalytic activity for the oxygen evolution reaction. So it's refreshing in that sense. I want to quickly go over the significance of OER. So at this time, it's predicted that by 2040, the carbon dioxide emissions will almost double compared to their state in 2000, and our reliance on the fossil fuels are almost 80%, and is predicted to stay around that area in the predicted range according to the International Energy Agency, and our energy needs only increase. So it is very important to liberate the energy industry or find renewable alternatives to fossil fuels. So on this note, electrochemical catalysis becomes very important because most of these alternative and clean energy technologies or chemical processes that are potentially going to be better for the environment, they require improved catalysts, and electrochemistry is an essential part of most of these processes. So we need high performance catalysts for a cleaner future. The traditional descriptor based approach that I just mentioned, I'm going to quickly go over it. It is based on the Sabatier principle, which is basically a seesaw of regarding the availability of the particle surface, the catalyst surface. So there's a optimal binding region based on a descriptor, which requires that whatever is a significant species only relates to that surface in an optimized way such that it doesn't take up time in the kinetic mechanism from other steps, but at the same time it stays long enough on the surface for it to fully develop into the next species. So this descriptor-based approach comes in these three stages. It can either be performed through experimental means by picking one by one and performing experiments one by one for the candidate materials, or by developing permutations of the candidates in a modeling environment and performing simulations and predicting the binding energies or whatever that we're looking at, and then suggesting an optimal activity zone. An overview for the oxygen evolution reaction. This one is an acidic environment that is 4 steps. It's very similar when it's in basic environments. Because the mechanism is so complicated, it has been concluded by previous studies that both oxygen energy and hydroxide binding energy are required to understand the catalytic activity and to optimize the catalytic activity. So the potential, the thermodynamic potential for this process is 1.23 volts. And there is a significant anode potential even with best catalyst, which means that we still don't have a good catalyst for this reaction. So in the past, platinum was used. Now, recently, through computational tools, there are better candidates. One of them is an iridium-based oxide, and one of them is a ruthenium-based oxide. These oxides, interestingly, they have been first developed through computational means, and then they have been proposed to experimental groups, and then it was confirmed that they are good catalysts for the process. But now it is a very interesting area to pursue even cheaper catalysts, even less precious catalysts that can potentially create more affordable renewable technologies. So one of these peroxides that are suggested for our oxygen evolution reaction is called BSEF. An interesting fact about the perovskites, they were named after a Russian scientist called Lev Perovsky. So, however, perovskites are reported to have competitive catalytic activity when they're compared with precious alternatives. So, this particular perovskite, the BSCF that we just mentioned, this guy over here, the Suntivich and their colleagues predicted that through their descriptor-based systematic analysis, they have predicted that BSCF can potentially catalyze OER with intrinsic activity and with at least one order of magnitude higher than the iridium and ruthenium based alternative, and with a small over potential of 0.35 volts. So it's going to be high level electronic details, but Suntivich and their colleagues predicted that through the systematic examination that BSCF owes this high OER catalyzing activity to the 3D electron occupancy which the OER reaction requires, and it also exhibits high covalency amongst the transition metal oxide bonds, and this is why there's an enhancement in the activity. And later on, Chan and their colleagues recorded almost a 2 orders of magnitude enhancement through experimental measurements in the performance of the OER catalysis. So now we can come to this paper. Now we know the background. This paper by the Schmidt group. They have previously dealt with this material, and they have manufactured it through a different method. And now they want to look at how the ball milling is going to affect the activity, because it's documented by other groups that ball milling of peroxides can enhance catalytic activity. So they want to give it a shot, basically, and they also feel that activity will drastically get influenced by the structural changes and chemical changes that can take place by the method of preparation of the catalyst and by the milling itself, the mechanical mechanical processes. So they have an elaborate preparation that I would not like to go through in detail, but basically they mix the stoichiometric quantities of the ingredients and they put it in an environment that's conducive for preparation. And once the powder is formed and it is being calcined, they ball mill it. And they do it in a very specific way. And once it's ball milled, they ball mill it in increments. They don't mill it all at once. They mill it for a certain amount of time and then stop and then mill it again. And once it's been milled, they introduce the milled particles to carbon fibers and then they ball mill them together. So in the previous study they have only once they have ball milled the BSCF, and once they have separately ball milled the carbon fibers, they have mixed them with each other, and they did not ball mill each other. So they're curious about how this is going to play out. They have various characterization methods. It's a very abundant experimental group, it appears to be. They use XRD for phase identification. They use BET for determining the surface area, and they use HRTEM for morphology and surface structure, and XPS and SEM to look at the microstructure. And then they also resort to other spectrometry tools. And when it comes to the electrochemical characterization, they use two methods. One of them is a rotation disk electron method, and then they also use a Teflon fuel cell to investigate the OER activity in a basic environment. So here we have this, let me go through, we have the SEM, the XRD, and we have the rotation disk electron set up here, and then it's just a rough estimation of a fuel cell we have here. So when we look at the structural results, let's identify what these are first. So this, when we say the BSCF pure form, the milled one is also cured, but it is after the preparation and after the calcinification, calcining of the material. And when we say milled, it is the ball milled version of the prepared perovskite. And when we say BSCF/CF, it refers to the ball mill particles being mixed with carbon fibers and then being ball milled again. So when we look at these, the patterns of diffraction, we see that the BSCF and the ball mill BSCF have the same pattern, which is expected because there is, it's not predicted to have too much of chemical structural difference. But when we look at the BSCF-CF ball milled sample, which is mixed with carbon fibers, we see that there's definitely a difference in the pattern, number one. Number two, there's a higher level of noise. Number three, the peak is slightly shifted. So these three indicate a structural change, a chemical change. So when in table 2, when the lattice parameters are calculated from this data, it's seen that lattice structure has been altered as well. So this brings us to the point that carbon, the addition of carbon, must have done something to one of the metals, potentially cobalt. So they think that the oxidation state of cobalt has changed, and it has led to this change in the pattern that we see. And when we look at the results for the images for the surfaces, we see that there is a change in morphology. The unmilled BSCF has agglomerates. In the milled version, we don't see agglomerates. So the agglomerates are gone. There is not much of a change in the size. There is only a 1.3 times difference in the size and in the surface area, although the size is slightly smaller. As per a detail, the population of particles that are under a certain range have been increased, but it is not enough to increase the surface area too much, because the increase in the surface area is only 1.3 times than the unmilled sample. And when we go look at the electrochemical characterization results, we see that, well, they have performed several techniques here. They have performed cyclic voltammetry and chronoamperometry. I'm not going to go through all of them, but cyclic voltammetry predicted a voltage of 1 to 1.7 volts, and then the one we see in the figure 6, this one has resulted in a 1.55 volts. So what we see is there's almost, this one is a logarithmic scale, there's almost a 20 times increase in the milled particles compared to the unmilled particles. So when we go back, the surface area only increased 1.3 times, and then the performance, the activity, is increased 20 times after milling. So this can't be just only because the size decreased and surface area has increased. This must be something else. So there are what they're suggesting about this is they're suggesting that there must have been a change in the surface such that it has favored the OER and it has led to this improvement. And they're saying that there was a surface layer with a short range order was created, and they are also seeing that there might be a hint of amorphization, and it has been a theory that amorphization of surfaces might be leading to increased activity. So there are these two surface related phenomena that we're looking at, and so in conclusion, ball milling of this particular peroxide will significantly increase its OER activity for the oxygen evolution reaction, and it stems from the formation of a surface layer with a short range order, and not necessarily simply because of a decrease in the particle size. And also when we compare the OER activity of BSCF with carbon and without carbon, we see that by acting as an oxidizing, reducing agent, it functionalizes the BSCF. Although it doesn't participate in OER, it makes the catalyst more active. And this also increases the activity. So if we actually combine these, like superimpose these two approaches, a functionalization through carbon and an enhanced surface structure through milling, we can potentially create a very promising OER catalyst. So thank you for listening. It's Deniz, Yildiz.